Alright, figured I'd start this late show early. 30 minutes early, but right now I'm on another character. You know, it's just from a private session. Has no real objective, but I figured people would want to see gunplay. Or I'd figured on showing it. Since I'm in the town currently, I thought, hey, the title of this thingy, perfect. I guess that's as good a place as any to stop it. Stop this damn. I turned off number lock. That's why. Okay, there we go. Accidentally turning off number lock. It takes lives. Never do that. All right. Always remember to turn on your number lock. Unless you use that the number pad for navigation like a fucking Neanderthal. I don't know. So yeah, what I'm doing here is just wasting ammo, because you know, if you use it or lose it. And I recently got 2 strength on this character. His name is Grill Bears. He's hungry. Born without strength. He's basically just survival. It's meant to do survival, but I recently was able to uncap my rifle, handgun, and archery. So you know, I've been saving all that ammo up, and it goes bad. I'm just sniping puppets from this crane. Right. Fuck. Very first shot I do, it's like, okay, I'll stop doing fancy shit. I don't know. Fucking asshole. Well, that's one way to waste ammo, I guess. Just miss everything. I don't know what it's about. Maybe it's something about the trees that trip me up. Maybe it's because I don't know. Jesus. I'm bad. Let me just see what range this is. Okay. I wasn't sure of that. Yeah, I got him. Whatever, it's early in the show. No one's clicking on this. Nobody's seen me miss. It's gonna be nothing but, perfect shots from now on. That's what it's gonna be. I do know that, where is it? Is that it? No, it's that stadium. That has a lot of equipment in it. But that's what the, why the fuck? It just hides my icon for the RPK, but I got the RPK, and I'm gonna go charging in there. It's got demo puppets, it's got, I don't know, lots of puppets. It's unsilenced, so it's gonna draw puppets from everywhere in the city. It's gonna be a great time, but for now, we're just taking our little Hunter 22 and having a little bit of fun. Listening to the radio, eating tuna salad MREs. Should I? Where are we there? I have plenty of MREs. I think I ate beef stew last time. Let's just eat a tuna salad. Why not? Since we're hungry. Waiting for puppets to show up on our SCUM. There's one. Why are they spawning over there? Because, you know, they used to be swarming around this supermarket. Now I guess the spawners those spawners are done, and now the cool spawners are by this, whatever it is. I guess it's about 200-ish. Yeah. I guess the 22's trajectory is pretty flat. I don't know, I haven't been paying attention really. Just been plinking. Some good old plinking. Jeez, okay, this is bothering me. There's some white space. Don't worry about it. Okay. There was a puppet there earlier.
Welcome to the Thunderdome, bitches. John
Gosh. Obviously, one wrong move and I'm toppling. But there's one. There's one.
Let's play some tunes.
I forget where it is. I think the aorta goes to the left and the vena cava is on the right. I don't remember. No. Don't quote me on anything. I figure I haven't nearly gone into third person. Look at that. I got a nice little pirate hat. And everything. Anyways. Okay, just have more 22 to waste. More 22. Mostly 9mm is what I gotta use. I don't know, I probably shouldn't leave. I probably will leave the car at the gas station. And then, you know, walk everywhere throughout the city. Then again, no, if I get, you know, good military hardware, it's just I might have enough room in my hiking backpack, but I don't know. Yeah, we'll risk it. We'll risk it. Don't want the noise of the car driving through the city to attract the palpits. But that does mean if I get hit, I'll be cut off from medical supplies. The best I'll have is absinthe. It'll be fine, though. We'll be doing fine. Oh, we just need one more shot. Probably took his neck off. Okay, I think we'll leave the hunter there. Now we'll descend into the true operation. And hope that the ladder cooperates. I don't expect it to not, but you never know. Ladders in this game can be a bit finicky. Like, whew, imagine if it dropped us down there. Let me see if I can. Yeah, I don't mind. RPK. Let's see how much ammo we have in our RPK. 65. Not like I'm expecting to run out of anything in the RPK anytime soon. But never hurts. Never hurts to know. It's just the long climb day. Alright, and that is fresh water flowing through. Oh boy, she's made. As long as she's not waiting down there for me, I guess. And I think this is the kind of place I'll have to go. I'm going to have to find bricks or cement or something for Bob. I don't know, there are bricks lying around here. That's probably important for something in the base. I don't know why else they'd be extant. But, it's just them. Let's free up some space in the car, because we can repair our hunter with... Let's just make sure we don't accidentally use that. We got... one of our lesser hunter. Oh, come on. Stupid box of ammunition. Okay. We're doing fine. Repairing our hunter with spare parts. Good as new. Find so many hunters. So now we're doing just fine. Let's take the mag with us. Put it in our quiver. Make room in our quiver for an RPK magazine.
Glad to tour you with combat as always. I'm your host, John Dick. Welcome to SCUM.
Let's go here first. Let's just visit the supermarket first.
Deathmatch, capture the flag or cargo. And don't forget, the bears are more afraid of you than you are of them.
See if we can look at events. Team Deathmatch, just MMA. Military polygon. Sure. I don't know what any of these are, but I wonder what this place is called. Yeah, tis no. Get deathmatch at the sawmill. A random battle. Yeah, it seems like there's no deathmatch that happens in this city. No, that'd be pretty neat, I think. Go back, see what's on the roof. I'm thinking maybe a game mode where you hunt down, like search and destroy. This is too big for that. Just have someone hiding in a building or something. I don't know what you could do here. Maybe this city's too big. It ain't big enough for the both of us. Okay, I missed the ladder. Oh yeah, okay, it's here. I'm silly. There we go. Okay, that's more for going down. You can get up on the side here. Yeah, you could make a deathmatch in the supermarket, just like little parts of the city. I don't see any other reason for this supermarket to exist. Yep. Search from here. Why not? Hey, lucky angle. I guess this is a supermarket and not a grocery. Yeah, whatever. I should probably be more conscious of direction. Yeah, there we go. Ah, finally, somebody who doesn't have obsessive trigger discipline. Or maybe it's because I have low skill in handguns, and when you get higher skill, you actually learn trigger discipline. And that's just a little thingy they hid for you. I don't know.
John Dick here, thanking you for joining us for another glorious battle. If you're tired of withering in obscurity,
Alright, I think I want to search that building. See what's in there.
fame and prestige, or die trying, or both. Let's play some tunes, shall we?
This place certainly is hiding stuff. I wonder if in multiplayer does this just like turn into people camping different little resource spots with their bases. Pretty soon it's just a city of bases. Bet they don't establish trade routes, probably. You could probably live your whole life in this place. Got fucking sardines, why not? You just got fresh food here. Freaking neato. But you don't have a plane. How far is this place from the airport? Yeah, pretty far from the airport, actually. And I know the place like this is place in the mountains. Yeah, observatory. Neat little place, neat little place. I suppose that counts as clearing out the gas station, right? There's probably more. These are the kind of encounters we're going to be able to expect, I think, all across the city. Just because I turned up the puppetry so much. It's good for getting all that ammo used up, because Jesus Christ, I've just been showered with 9mm. Yeah, 9mm all the time, all the way, every way, just boxes 9. I forgot. I think 9mm is 357. Right, normal. Or maybe it's like slightly smaller. I'm forgetting. But I know it's around that caliber somewhere. And for some reason, the 357 Magnum is just, 357, not, 9mm. Probably because metric is for, well, let's just say un-American people. And anyone who is an American doesn't matter. That's the best euphemism I've got.
Kill or be killed. That's how it works here on SCUM Island, start your day.
on an adventure we go. Yet more 22. I didn't find anything particularly important.
Welcome to SCUM Island, where survival is the name of the game. Mass murdering maniacs have decimated each other for fame and fortune. I'm your tour guide on this journey down a river of blood, John Dick. Let's do this thing. We've got some interesting events for you to check out. Try your hand at deathmatch, capture the flag, or cargo drive. And don't forget, the bears are more afraid of you than you are of them.
Have you heard about summer snow when it falls on you? But don't you sweat your pretty skin, 'cause it melts away for it sinks in. And you dream about this very night when the moon runs down the summer sky. Could it be the morning of the spring when the sea runs dry and starts to sing? Have you heard from the sky? Down near the high tide goes around it. Through the whispers of pines I hear them sing. The more you love, the more you live. Do you ever feel like going back? Nothing seems to be you read until your legs gave way, and you cried and got back up again. And it's real to think that I could fly across a broken bridge in a fading light. Never thought ahead of my 2 feet. Never had a care in the world, you see. Have you heard from the sky all about it? Down near the high tide flows around it. Through the whispers of pines I hear them sing. The more you love, the more you live. Have you heard from the sky all about it? Down near the high tide flows around it. Through the whispers of pines I hear them sing. The more you love.
This police station is even more stocked than the usual one. Too bad I leave all my lockpicking stuff in the car. Not that I expect to find anything special here.
I'm free from living lies, free from my own deception.
I guess the clink means it can't be a bad round, because bad rounds don't clink. It's either a stovepipe and... Okay. I think there's a simple process for figuring these out.
You, my friend, look like somebody who could use a bit of action. You came to the right place. I'm your host, John Dick, and welcome to SCUM Island. Once you're ready, be sure to sign up for one of our mini events. Challenge yourself against other prisoners. Team up and overcome for blood and glory. And don't forget, the bears are more afraid of you than you are of them.
Alright, let's continue on our way, searching this place for stuff, man. Looks like Tech 1 caused havoc in this place.
Greetings, friends and enemies alike. You came to our humble island for some peace and quiet. You came to the wrong place. I'm your host, John Dick, and I'm here to tell you that things are about to get downright brutal. Our producers have lined up some amazing tournaments for you. Sign up and revel in the glory, or die like a worm. The choice is yours. Let's get some music on to set the mood.
Oh, come on. Can't use it. Just have to fall through. What the hell'd you get in there? That's the toll. Oh fuck, I left the weapon repair kit in the car. God. Okay. Okay, I'm stupid. I think I have M9 parts at home, actually. Maybe this is fortunate that I didn't waste my repair kit on something that, you know. Whatever.
The host with the most, John Dick, welcoming you to yet another fierce blood match. We've got some interesting events for you to check out. Try your hand at deathmatch, team deathmatch, capture the flag, or cargo death. Let's play some tunes, shall we?
I summoned the piss demon. I guess you could use this if you have custom files. You could, I don't know, play for everyone. This is a neat little place.
Welcome to the Thunderdome, bitches. John Dick here, inviting you to join in on the fun as our prisoners disembowel each other.
Pat his head. What a
The best way to communicate is
long-necked friend.
what are you waiting for, Scrub? Sign up and rank up.
Yeah.
Now get out there and paint your town red.
Yeah.
Make your mama proud.
Uh-huh. Oh, okay. He was nodding vigorously. Don't really know what I'm looking for in here, but I'm in here. Metal saws are always helpful, I guess. Yeah, actually, that's not. We're getting full. All right. Should maybe start charting a way back. Chart the horse. Maybe we don't use our AKM here, but we still have a lot of 45 ACP to use up. And I like my M1911 more anyways. Such a stylish gun, just something about it, you know. Just face through the fucking wall. so we're going that way. I'm pretty sure. Unless there are like multiple cranes. Westward. No, there are multiple cranes. We came from like southeast. Alright.
Do you think I'm sexy?
Yeah, murder is fun, but if you tried the Indian food, shit's amazing. I'm John Dick, and today's match is brought to you by Pong's House of Curry. So good, it'll make your asshole bleed for weeks. If you're tired of withering in obscurity, you can register for one of our glorious events. Gain fame and prestige, or die trying. Or both. Keep your head out there, players, and try to collect a few extra heads along the way. Here's some kick-ass music to start your day. Sing it like ooh, if you want to. The next time I turn around, you'll have grown into a woman in a single bound. I hope I never take you for granted. Spending time with you is all that I wanted. But I'll go back to when you were small, burning our favorite records on the CD-ROM. We were splitting headphones in a hammock to a soundtrack we could get lost in. Sing it with me. Sing it with me. And we'll go howling at the moon. It's no use living if you're already there. It's not worth saying if it's already said. Even if it all goes over your head, believe it if you want to. So keep your eyes on the road and your head in the stars. Follow it down the rabbit hole just a little while longer. You can change anything if you want to. Sing it like ooh, if you want to. Sing it like ooh, if you want to. If you're scared of the dark, let the rundown street lights be your stars. Let them know who we are, let them shine for you. It's no use living if you're already dead. It's not worth saying if it's already said.
Thought I would overshoot for a second.
Believe it if you want to.
That'd have been horrible.
Keep your eyes on the road and your head in the stars. Follow it down the rabbit hole just a little while longer. You can change anything if you want to. Said it's not worth living if you're already dead. It's not worth saying if it's already said. Even if it all goes straight to your head, believe it if you want to. Believe it if you want to.
What a silly puppet.
Kill or be killed. That's how it works here on Scum Island. My name is John. I'd like to invite you to join us as our prisoners mutilate each other for fun and prizes. If you're tired of obscurity, you can register for one of our glorious events. Gain fame or die trying. Or both. Keep your head out there, players. And just collect a few extra. Here's some kick-ass music to start your day. Gladiatorial Combat Evolved. I'm your host, John Dick, and welcome to Scum Island. Once you're ready, be sure to sign up for one of our mini events. Challenge yourself against other prisoners. Team up and overcome for blood and glory. And don't forget, the bears are more afraid of you than you are of them.
Okay, now it's time to take a break before. No, yeah, because it's gonna be a drive home, and that'll break now. The video is about 3 hours long, and there's about 3 hours left of the stream, so I think we'll start with that. Just play through. Get on to Bob after we get home here.
For the tiniest increment of time that is possible to talk about, 10 to the minus 43 seconds. The temperature was 10 to 32 degrees, and the density downright indescribable. At that instant, there was only one universal force and one type of elementary particle. But it wouldn't last. At the end of this instant, gravity separates itself from the union. At 10 to the minus 35 seconds, the strong nuclear force exits the union as well, and this triggers inflation, the event where the universe instantaneously grew into size, from tinier than an atom to an unknown large size. This expansion and subsequent cooling down to 10 to 27 degrees allows 6 different types of quarks to form. At 10 to minus 12 seconds and 10 to 15 degrees, the weak force and electromagnetism separate, and we have the 4 independent forces we know today. At this point, all 6 types of leptons have formed, including the electron. At 10 to the minus 6 seconds, up and down quarks have formed protons and neutrons. All heavy quarks have decayed. All heavy leptons have decayed. All antimatter has disappeared. And by the time the universe is only 1 second old, protons and neutrons are already getting together to form the lightest atomic nuclei.
Wait! Can you slow down and try that again?
Sure, Diana. Can you tell me the difference between force and matter?
Well, sure. Matter is stuff that you can hold in your hand, or at least visualize holding in your hand. And a force is something that causes matter to move, change, or react, an action. Air is matter, even though you can't see it unless you're in Los Angeles.
Pretty good. Now, consider a piece of matter, and imagine taking it apart down to its basic constituents, the particles that make it up, down to the atoms, and further down to the protons, neutrons, and finally to the quarks and electrons. If our hands were small enough, we could hold them in our hands as well. So, these particles pass your
cheesy.
hold it in your hand matter test and are declared matter. But at this level of tiny, things get a little fuzzy. Watch this.
As we take apart matter, down to the smallest scales, we must pass through levels of structure that are only possible because of forces that hold these structures together. The proton and electron, for example, are attracted to each other, and that force of attraction is what holds them together in the atom. But what is it really that causes this attraction? How does the electron know the proton is there? And what draws it towards the proton? How does the electron know not to be attracted to the neutron? The answer is that the electron and the proton each fill the space around them with countless millions of other tiny particles that have only the most ephemeral existence. Because it is electrically neutral, the neutron does not. These particles come into existence only briefly and are gone, only to be replaced by another one thrown out by the parent particle. On this scale, the tiny bit of energy that is needed for the existence can be created out of nothing. But they also must disappear in the briefest instant, because the energy used to create them can only exist for a very brief instant. You can imagine these virtual particles as balls tethered to the parent particle by a rubber band and snapping back to the parent when they disappear. If one or more of them should encroach upon the territory of a virtual particle tethered to another parent particle, they can get entwined and exchanged. Such an exchange is felt by the parent particle as a force.
These fields of virtual particles surrounding a parent particle are created in very specific patterns and fill the surrounding space in a well-defined way, and scientists cleverly call them fields. The virtual particles are called carriers or mediators of force.
Scientists recognize 4 distinct kinds of force fields, and they all work through the mechanisms described above. You are readily familiar with 2 of these forces: gravity
And electromagnetism.
and electromagnetism
Hey, I got it.
operate on a scale that we encounter in our everyday life. A third force causes quarks to stick together in protons and neutrons. And a residuum of this force causes protons and neutrons to stick together in the nucleus of atoms. This force is called the strong force, or sometimes the color force. The fourth force causes radioactivity and is called the weak force. The virtual particles that make up these fields and get exchanged in each force are called gauge bosons. And each of the 4 forces has its own gauge boson. Within limitations, energy and mass can be created out of the nothingness of space-time, but only for a very brief instant. And the more energy and mass these virtual particles have, the shorter must be the time that they can exist before snapping back to the parent. Lighter gauge bosons can exist for a longer time, and these in turn can get further from the parent before they must return. So the range of a force is directly related to the mass of its gauge boson. The photon is a gauge boson for the electromagnetic force, and the graviton is the gauge particle for gravity. Both of these particles are massless, and so the range of these 2 forces is unlimited.
Just had to lower the frickin' volume. We're starting to
The
grate.
strong force is much more complex. The charge property responsible for the force between quarks comes in 3 distinct states. Not just 2, like the positive and negative charge states in electromagnetism. So in a loose analogy to the 3 primary colors, red, green, and blue, the 3 kinds of charges in a strong force are usually referred to as color charge, and are designated red, green, and blue. Since the theory of electric charge is dubbed quantum electrodynamics, or QED, the name for quark theory has become quantum chromodynamics, or QCD. It is interesting to note that all observed particles are white. Color is never visible. And since the proton and its baryon cousins each have 3 quarks, the color possessed by the 3 quarks must be 1 each of red, green, and blue, which sum to white. And mesons are always a quark and an antiquark pair, containing colors of red, anti-red, or blue, anti-blue, or green, anti-green. Also combinations that equal white. The strong force, of course, must have its own gauge boson, and it turns out that there are 8 of them. 8 different gluons that carry the color force. And unlike the other force carriers, gluons have a color property themselves, and therefore interact with each other. Every time 2 quarks interact and exchange a gluon, they swap colors. Also,
Alright,
because
time to get
gluons
to,
are attracted to each
Get
other,
back to Bob.
it is possible to have a gluon collection, which is referred to as, what else, a glue ball. The interactions that result from the weak force are incredibly short-ranging. They are effective over a distance even smaller than a proton's diameter. And this accurately implies that the weak force gauge particles, called the W and the Z, are immensely heavy. Over distances small enough and at really, really high energies, the 4 forces are indistinguishable because their respective force particles are also indistinguishable. The standard model of physics combines QCD with QED and the weak force theory. It states that there are 6 quarks and 6 leptons and 12 gauge bosons, as well as their antiparticles. But only the up and down quarks, the electron, and the lightest neutrino are populous today. In the standard model, the entire system of matter and forces, except gravity, is encapsulated in a few simple equations and is organized around one core principle, known as local gauge symmetry. Amazing.
Okay, now do you want to tell me what you told me before I told you to tell me slower?
Sure. Let's go back to the birth of the universe. Things are hot. Real hot. And things are happening fast. Real fast.
For the tiniest increment of time that is possible to talk about, 10 to the minus 43 seconds. The temperature was 10 to 32 degrees, and the density downright indescribable. At that instant, there was only one universal force and one type of elementary particle. But it wouldn't last. At the end of this instant, gravity separates itself from the union. At 10 to the minus 35 seconds, the strong nuclear force exits the union as well, and this triggers inflation, the event where the universe instantaneously grew into size, from tinier than an atom to an unknown large size.
You know, that talk about quantum color theory doesn't really
This
clarify
expansion
this.
and subsequent cooling down, 10 to 27 degrees, allows 6 different types of quarks to form.
Oh, I guess they defined forces in
At 10
quarks.
to minus 12
Okay.
seconds and 10 to 15 degrees,
I get it.
the weak force and electromagnetism separate. And we have the 4 independent forces we know today. At this point, all 6 types of leptons have formed, including the electron. At 10 to the minus 6 seconds, up and down quarks have formed protons and neutrons. All heavy quarks have decayed. All heavy leptons have decayed. All antimatter has disappeared. And by the time the universe is only 1 second old, protons and neutrons are already getting together to form the lightest atomic nuclei. This is how we represent an electron visually. The particle itself is a fundamental particle and is...
Yeah, I gotta stop here because I did end up watching the minute physics video on my own. It was just like I said. He went over the visualization of the electron cloud. Like, oh, this isn't actually a cloud. It's a probability of where the single electron could be around the atom, and all sorts of different orbitals. Like, you should have learned this in school. And yeah, it's not worth going over. Anyways, back to the video.
too small to be seen by any imaginable instrument of observation. So we instead represent the properties that allow the electron to interact. The central small dot represents the weak charge of the electron. This charge, entirely separate from electric charge, gives rise to the weak nuclear force. This force causes radioactive decay, and its typical range is much smaller than the diameter of a proton. The larger volume of shifting purple is meant to represent the electric charge of the electron. This charge is the generator of the electromagnetic force, which has infinite range, although the drop-off of strength is pretty dramatic as we move away from the electron. The electromagnetic force is how electrons interact with other electrically charged particles and with magnetic fields. These interactions make the structure of atoms and molecules possible. This gives rise to almost all of the complexity that we see around us. This is how we represent the up quark visually. The particle itself is a fundamental particle and is too small to be seen by any imaginable instrument of observation. So we instead represent the properties that allow the up quark to interact. The central small dot represents the weak charge of the up quark. This charge, entirely separate of electric charge, gives rise to the weak
by the way, all these
nuclear
particles
force.
are represented by dots.
This force causes up quarks and down quarks to swap flavors, and its typical range is much smaller than the diameter of a proton. Surrounding that is the volume depicted as gold for the up quark. This represents the electric charge of the up quark, which has a positive charge of plus 2/3 units. The electric charge is the generator of the electromagnetic force, which has infinite range, although the drop-off in strength is pretty dramatic as we move away from the quark. The larger volume of shifting red, green, and blue is meant to represent the color charge, which generates the strong nuclear force. This is a force that holds quarks together in a proton or neutron. And a residuum of this force holds the proton and neutrons together in the nucleus of an atom. This force is 100 times stronger than the electromagnetic force, but its range is limited to about the size of a proton. This is how we represent the down quark visually. The particle itself is a fundamental particle and is too small to be seen by any imaginable instrument of observation. So, we instead represent the properties that allow the down quark to interact. The central small dot represents the weak charge of the down quark. This charge, entirely separate of electric charge, gives rise to the weak nuclear force. This force causes the down quark to change into an up quark, and its typical range is much smaller than the diameter of a proton. Surrounding that is a volume depicted as purple for the down quark. This represents the electric charge of the down quark, which has a negative charge of 1/3 units. The electric charge is the generator of the electromagnetic force, which has an infinite range, although the drop-off in strength is pretty dramatic as we move away from the quark. The larger volume of shifting red, green, and blue is meant to represent the color charge, which generates the strong nuclear force. This is the force that holds quarks together in a proton or neutron, and the residuum of this force holds the protons and neutrons together in the nucleus of atoms. This force is 100 times stronger than the electromagnetic force, but its range is limited to about the size of a proton. This is our depiction of a proton. It is composed of 2 up quarks and 1 down quark, as you can see from the tiny rings of color near the center of the quark. The overall charge of a proton is positive, and so we have given it a gold shell. Note that we can simply add the charges of the individual quarks to get the charge of a proton. The red, green, and blue colors of the quarks represent the color charge which generates the strong nuclear force that holds them together. It comes in 3 different charges, represented here by 3 colors, and for different colors, force is attractive. The mediator of the strong force, the particle that is exchanged in an interaction, is a gluon. We represent gluon exchange as the occasional wispy string between the quarks. As you can see, the gluons have color themselves, and each gluon exchange causes the quark involved to swap color. Although we show quark motion inside the proton as leisurely, they are actually traveling close to the speed of light. Oh, protons taste sour, like vinegar and lemonade.
That is very helpful to me. I always wanted to taste protons.
This is our depiction of a neutron.
So
It is composed of 2
neutrons
down
taste
quarks
bitter, I'm
and
guessing.
1 up quark, as you can see from the tiny rings of color near the center of the quark. The overall charge of a neutron is neutral, so we have given it a silver shell. Note that we can simply add the charges of the individual quarks to give the charge of the neutron. The red, green, and blue colors of the quarks represent the color charge which generates the strong nuclear force that holds them together. It comes in 3 different charges, represented here by 3 colors, and for different colors, the force is attractive. The mediator of the strong force, the particle that is exchanged in an interaction, is a gluon. We represent gluon exchange as the occasional wispy string between the quarks. As you can see, the gluons have color themselves, and each gluon exchange causes the quark involved to swap color. Although we show quark motion inside of the neutron as leisurely, they are actually traveling close to the speed of light. This is how we represent a neutrino. The particle itself is a fundamental particle, and is too small to be seen by any imaginable instrument of observation. So we instead represent the property that allows the neutrino to interact. The white area represents the weak charge of the neutrino. This charge, entirely separate of electric charge, gives rise to the weak nuclear force. This force allows the neutrino to interact, but only very weakly, and its typical range is much smaller than the diameter of a proton. Neutrinos are produced when a down quark decays into an up quark and an electron. Conservation laws require that a tiny neutral particle is created in beta decay. And the particle is the neutrino. Well, technically, it's an antineutrino. Because the neutrino only interacts through weak force and negligible gravity, it almost never interacts with other particles on its own. Millions of neutrinos stream through your body every second, totally unnoticed and unnoticeable. Gluons mediate the strong force. They have no mass, no electric charge, and no weak charge. So depicting gluons visually is a real challenge. To begin with, there are 8 of them, and each carries a combination of color charge. Secondly, there are no free gluons. They exist only virtually when 2 quarks interact. Third, since gluons have their own color charge, they generate secondary virtual gluons. these generate other gluons ad infinitum. This means there's such an ongoing storm of these gluons that the whole process is impossibly complicated. But undaunted, we press on. We know that when gluons cause two quarks to interact, the quarks swap color. And since color is conserved, the gluon must have at least two colors of its own. Next, we know that the strong force mediated by the gluons increases the strength as the quarks get further apart. This means the gluon field is what is called a flux tube, and this leads to a gluon shaped like a string. Putting all these ideas together leads to the depiction you see on the screen. Photons are the gauge bosons, the force carriers for electromagnetism. Whenever charged particles interact, photons are exchanged. They have no mass, no electric charge, no weak charge, no color charge. The epitome of almost nothing at all, and yet here is where it's at. Since they are responsible for all electron and proton interaction, everything we do in our everyday life, from moving a mouse to running in the park, relies on the exchange of photons. They are energy contained in shifting and changing electric and magnetic fields. Like all particles with no rest mass, photons travel at the speed of light. They cannot come to rest. Photons, in the range of visible light, carry just enough energy to excite a single molecule in a photoreceptor cell of your eye. Weak bosons, also called intermediate vector bosons, are the exchange particles for the weak nuclear force. There are three of them, called W+, W-, and Z0. They are very massive, each being 80 to 90 times as heavy as a proton. Because they are so heavy, the uncertainty principle allows them only an extremely short range when they act as force carriers. So the weak nuclear force has a range about only 1/100th the diameter of a proton. The W bosons cause quarks to change flavor, while the Z has an effect in an esoteric type of interaction called neutral currents. Gravitons are the as-yet undiscovered force carriers for gravity. Because of the great success of the Standard Model in describing the other three forces which exchange bosons, it is assumed that gravity has a gauge boson as well. Its properties have been extrapolated. It is a massless, stable, spin equals 2 particle that travels at the speed of light. Gravitons may not be constrained to the dimensions of space and time that we experience. Today we will talk about the mechanism that causes fundamental particles to have mass. If the electron had a different mass, then the orbitals inside atoms would be a different size, and the world would be a very different place. Let's begin by talking about the thing that physicists call a field. The need often arises to describe something that can have a different value at every point in space,
I lost all the treatment.
like the air temperature, or like the wind velocity,
I'm silly.
or like the strength and direction of some force, such as the Earth's magnetic field. There are only 4 forces that we know of.
Wait, never mind.
And they are all described by fields that give their strength and direction at every point in space. But take note that a force field is something real. It is not just a number for every point in space. It has a physical reality. As John Archibald Wheeler said, it occupies space. It contains energy. Its presence eliminates the true vacuum. And in the words of Feynman, the field creates a condition in space. In classical physics, these fields were often thought of as continuous, smoothly changing entities. But quantum mechanics rejects the notion of continuous, and so fields become distributions of tiny field particles. And the strength of the field at any given point was nothing but the density or the quantity of field particles at that point. These particles are called virtual particles because they violate the conservation of energy rule for extremely short times in order to exist. They exist because of energy fluctuations allowed by Heisenberg's uncertainty principle, but they must disappear quickly because of the same principle. In force fields, like electric or magnetic fields, these field particles are called gauge bosons. They are the physical reality that occupies space as described by Wheeler. And while gauge bosons exist as virtual particles when generated in violation of conservation laws, they can exist as real particles too, if they are given enough energy to satisfy the conservation accounting. Most fields in science are generated by some source. An electric field is generated by an electric charge. Take away the source, and the value of the field goes to zero. And Feynman's condition in space disappears. But the Higgs field is different in this respect. It still has a value, a physical reality, at every point in space, even without a source to generate it. So there really is no empty space anywhere. The entire cosmos is saturated with Higgs field all the time, everywhere. And because of quantum mechanics, this means there has to be a field particle. Enter the Higgs boson. Virtual Higgs bosons are the quanta of the Higgs field, and they interact with all particles except the photon, the graviton, and the gluons. The interaction between the Higgs boson and each particle is directly related to the rest mass of that particle. Since the top quark has the highest rest mass, it also has the strongest interaction with the Higgs. The electron is 300,000 times less mass than the top quark, so its Higgs interaction is much smaller. And the almost massless neutrino has only a tiny interaction. Since the Higgs permeates all space, any particle that interacts with the Higgs interacts with it all the time and everywhere. The Higgs particle acts like sticky bits that put a drag on other particles, and it is this drag that we detect as rest mass. In order to detect a Higgs boson in the laboratory, we must create a real one instead of a virtual one. We do this by slamming particles and antiparticles together to create fireballs of terrific energy. And out of this fireball, we look for decay products that indicate that we created a Higgs boson. There may be as many as 5 Higgs fields, each with its own boson. And hopefully in the next year or so, we will discover how many and how massive they really are.
It's giving us a story. This is meant to be watched, but, we're not going to watch it. So I guess enjoy the nice little intermission where they start saying relevant shit.
mechanics.
Do you two know how scientists identify the substances in distant stars?
They fucking
Do
guess.
you know how we measure the composition of the sun, for example?
They make it up.
Sure. One major tool is spectral analysis, isn't it? Yes, indeed.
I am familiar with the results of spectral analysis, but I am a bit unsure of how the spectra arise to begin with. Chaucer, is that part of our material for today?
Yes, it is, Diana. In fact, it is the starting point. Let's use Professor Peabody's Wayback Machine, since we don't have one of our own, and look at a little science history. Jeeves?
How in the hell did that happen?
Traveling to the 1750s, we find that scientists were putting different substances in flames and passing the resultant light through a prism. They found that the hot gases given off by the burning materials emit different colors of light or spectrum. For example, ordinary table salt generated a bright yellow spectra. Furthermore, not all the colors of the rainbow appeared. There were dark gaps in the spectrum. In fact, for some materials, there were just a few patches of light. By the 1820s, they recognized that spectra provided an excellent way to detect and identify small quantities of an element in a powder that was put into a flame. Meanwhile, the white light of the sun was also being examined closely. And in 1802, it was discovered that the solar spectrum itself had tiny gaps. There were many thin, dark lines in the rainbow of colors. But the reason for spectral lines in the light and the relationship to each substance was a real mystery. Traveling forward from that era to a little over 100 years ago, scientists were examining the colors of light given off by solid heated objects. They discovered that these hot solids gave off continuous
We're gonna get
spectra,
fucking copy
and that
struck
the
by
overall
Scott
color
Job.
of the light revealed the temperature of the object. Now, this was important because scientists realized that this discovery made it possible to measure the temperature of an object from a distance. They could measure the temperature of the sun, for instance. During these discoveries, they also noticed that some of the objects absorbed light extremely well, almost perfectly in fact. They were called black bodies because they absorbed virtually all the light that was shown upon their surfaces. These same objects also radiated almost perfectly, and as noted before, the temperature of the black body object determined the distribution of colors or wavelengths in the emitted light. This curve shows how much light of each color is emitted by a cool object. As you can see, there isn't much light, and what light there is mostly lies out past the red end of the spectrum, in the infrared. The figure on the right will show the different colors added together as we progress. Right now, only red light is visible. This curve shows how much light of each color is emitted by a medium temperature object. And the most light is emitted in the orange, yellow, green wavelengths. So now we add orange, yellow, and green to our cauldron of light on the right. As you can see, the combination so far looks yellow. This third curve is for a really hot object. Lots of light, and with most of it being emitted toward the blue end of the spectrum. And as you can see, our cauldron now is pure white in the center where all the colors overlap. A heated black body follows this color path as the temperature rises. A good example of black body radiation is the heat inside a kiln. Inside the kiln, electromagnetic radiation, light and heat, exist in a form of standing waves. Waves that, like the vibration of a guitar string, are attached at both ends. The ends of the standing waves, like the ends of a guitar string, do not move. They are anchored to the sides of the kiln. And many, many waves exist with varying wavelengths of color. At low temperatures, the primary color inside the kiln is the infrared, and we cannot detect it with our naked eye. But as the temperature rises, the kiln begins to glow red, and as the temperature continues to rise, the dominant color changes to orange, then yellow, then bluish white. The distribution of energy in light shifts to shorter wavelengths as the temperature rises. But there was a problem. The scientists expected the distribution of emitted light to continue to the increase at wavelengths toward the ultraviolet end of the distribution. It didn't. Instead, there was less and less light given off as they were further and further into the ultraviolet. This was called the ultraviolet catastrophe. But it wasn't a catastrophe at all. It was the beginning of something remarkable. A truly great scientist named Max Planck soon figured out a way to explain the observation. He concluded that the energy contained in the standing waves inside the kiln did not and could not possess just any and all different amounts of energy. Instead, the quantity of energy these standing waves possess had to be limited to a few specific discrete values of energy for each color. A standing wave of blue light, for example, can have energy equal to 0 electron volts, or 3 electron volts, or 6 electron volts, or 9 electron volts, and so on. In general, energy equals any whole number, n, times Planck's constant, h, times the frequency of light, nu, which for blue light is any number times 3 electron volts. But notice, blue light standing waves cannot contain energy equal to 1 electron volt, or 2 electron volts, or 4 electron volts. Realizing that energy could have only discrete values was the beginning of quantum mechanics. The energy is said to be quantized, and n, from the equation above, is called a quantum number. Planck's conclusion that light energy is quantized was quickly used by Einstein to explain another puzzling phenomenon. It was known that shining a light upon a metal plate can release electrons from the plate. But the light has to have a certain wavelength before a single electron is released. We can shine brighter and brighter light on the plate forever, but if the color isn't right, the electrons stay home. Einstein concluded that the light striking the plate had to be coming in discrete bundles, and unless a single bundle had enough energy to free an electron from its captivity, it would remain trapped. And as Planck had suggested, the wavelength and frequency of the light was a measure of the amount of energy each bundle carried. So while blue light packets might be able to free an electron, red light packets could not, no matter how many red packets hit the plate. But wait a minute. That sounds awfully like light is a particle and not a wave. And there are mountains of data showing light behaving like a wave. Diffraction, refraction, interference. Which is it, a particle or a wave? It is both. These light packets are extremely tiny. Let's call them photons, from Photos, the Greek word for light. And when you try to explain the behavior of things this small, you must resort to really unusual ideas. The ideas contained in quantum mechanics.
Now let's see how quantum mechanics helps us to understand atomic structure. Ah, Bohr and de Broglie are two of my heroes.
Boron who?
Cute, Diana. Cute. Jeeves?
It was during the early decades of the 19th century that the structure of atoms was coming into focus. It was known, for example, that a hydrogen atom contained one proton and one electron. But the scientists of the time could think of no stable arrangement of the two particles. It was known that a proton and any atom were grouped in a small central region called the nucleus, and that the electrons were somehow arranged in comparatively large distances outside the nucleus. But in hydrogen, if the electron were stationary, it would fall into the nucleus since the charges on the particles would cause them to attract one another. Yet the electron couldn't be in orbit circling the nucleus either. Circular motion requires consistent acceleration of circling body to keep it from flying away. But the electron has charge, and charged particles radiate light when they are accelerating. So an electron in a circular orbit would radiate light and would spiral into the nucleus. Niels Bohr proposed the first working model of the hydrogen atom. In the Bohr model, the electron circles the nucleus as if it were a planet going around the sun. And with a nod to energy quantization that Max Planck dreamed up for solving the ultraviolet catastrophe, Bohr said that inside the hydrogen atom, the electron was allowed to have only discrete values of angular momentum in its orbit around the nucleus. Translated, this means the electron can occupy orbits only at certain distances from the nucleus. And Bohr simply dismissed the problem of an electron radiating away its energy by stating that it just didn't happen. Even great scientists cheat sometimes. He postulated that inside an atom, electrons only radiate energy when they jump from one allowable orbit to another. And the energy of this radiation reveals the allowable orbit. The wavelengths of light absorbed by hydrogen when white light is shined upon it, as well as the wavelengths of light when it is subsequently re-radiated, had been precisely studied at the time but never explained. Here's a sample of an absorption spectrum and an emission spectrum. By predicting the value of orbits that an electron could have, Bohr's model also predicted the wavelengths of the lines in the hydrogen spectrum. And his model was tremendously successful. It explained in exquisite detail the atomic spectra of hydrogen. When the energy of the wavelengths of the spectral lines are compared to the energy differences in
All
orbits
this to tell us
allowed
how
in Bohr's
spectral
atom,
analysis works.
they agree exactly.
Like red shifts and blue shifts.
So the quantum approach worked
Really
well in
in-depth.
explaining the allowable orbits.
Might have to watch a few times.
But no one was certain
In the
why
free
only
time.
those orbits were allowed. In his doctoral dissertation in 1924, Louis de Broglie put forward a simple idea that significantly advanced the understanding of the extremely tiny. A quantum leap forward, you might say. Since Einstein and Planck and Compton
this better
had
be
firmly
0.
established that light could have the
This angle
characteristics
better be
of
0.
both a wave and a particle, Du Bois suggested that matter particles, protons, electrons, atoms, billiard balls, could sometimes act like waves. And when this idea was applied to Bohr's atom, it answered many questions. First, the allowed orbits had to be exact multiples of the wavelengths calculated for the electrons. Other orbits produced destructive
pretty much.
interference
Okay,
of
cool.
the waves, and soon the electrons couldn't exist there. So the circumference of the orbit must equal the wavelength, or twice the wavelength, or 3 times the wavelength, or for that matter, any multiple of the wavelength. Second, these orbits weren't really orbits in the traditional sense. These electrons didn't travel around the nucleus in a circle. Rather, they took the form of a standing wave that surrounded the nucleus entirely. The exact position and momentum of the electron particle could not be specified at any given instant.
De Broglie's particle waves seemed to answer many questions, but this was still not the final answer. No, the final answer is a brilliant piece of mathematics as well as physics. I agree. Jeeves, take it away.
A true giant of quantum revolution was Werner Heisenberg. And from the
You're
vagueness of
goddamn
positions of
right.
electrons in Du Bois' standing wave orbits, he drew a tremendous insight which he stated like this. The more precisely the position is determined, the less precisely the momentum is known, and vice versa. And while it may sound like a bunch of gobbledygook, it was the insight necessary to understand how an object can be both a particle and a wave. This single statement led to the understanding that subatomic particles can disappear and reappear in another place. And they can do this without existing in the intervening space. When an electron is trapped inside an atom, the places it can disappear and reappear include specific locations around the nucleus. And that makes it look like a shell. Basic particles can also be in more than one place at a time, if the time is brief enough. An electron can travel from here to there along all possible paths simultaneously. And even more astounding, these particles can appear out of the nothingness of space, exist for an extremely brief instant, and then disappear. Scientists call them virtual particles. They may be virtual, but they can have very real effects. All this jumping around makes particle description so inexact. But then existence itself is inexact at these tiny scales. The question is often asked, what is it that is waving when a particle is described as a wave? And after a lot of hem-hawing around the issue, the right answer is, existence is waving. The particle is jumping around, coming into and out of existence. And those places where the wave crests are maximum are the places where the particle materializes, most of the time. While the places where the crests are minimum are the places the particle avoids. The wave is a map of the particle's existence. And as the wave changes, the particle changes as well. While all important ideas necessary for quantum theory were established before him, it fell to the genius of Erwin Schrödinger to develop the equation that correctly describes the motion and behavior of all things this tiny. While Bohr and de Broglie managed to describe the hydrogen atom, Schrödinger's equation was able to describe hydrogen with the same detail. And then, it could go far beyond. It manages to account not only for the hydrogen atom, but it describes nothing less than all the atoms and all the elements in the universe. Schrödinger's quantum mechanics explains every element in the periodic table of the elements. The solution to Schrödinger's equation, called the wave function, is a fantastically accurate description of the real world.
Schrödinger's equation is really cool.
Yes, it is, Diana.
I agree. But can we talk a little more about Heisenberg's uncertainty principle? Isn't there more to consider than the approach we use to describe it?
Certainly, Kevin. Jeeves, let's have a closer look at that, please.
Werner Heisenberg did more than make a quantitative statement when he said that the particle's position and momentum could not be known simultaneously. He wrote an equation that quantified the relationship. Let's see how that information can lead to an easy understanding of the hydrogen atom described in exquisite detail by the Schrödinger equation. Without going into too much detail, let's look at a proton and an electron. Since the electron has a very tiny mass, it can occupy a very large region of space. Conversely, the proton has a very large mass, 2,000 times that of an electron, and therefore it occupies a very tiny region of space. The result is a quantum mechanical hydrogen atom, a tiny massive nucleus surrounded by a much larger cloud representing the electron. If we look at a simple graph relating the probability of finding the electron in a shell at a given distance from the nucleus, we find that as we travel outward from the nucleus, the probability increases at first as the shell expands. It reaches a maximum value and then decreases again as the electron cloud thins to almost nothing at large distances. Amazingly, the radius where the probability reaches a maximum is precisely equal to the radius of the first allowed orbit of Niels Bohr's model of the hydrogen atom. And its energy is exactly equal to the energy of an electron in this orbit in the Bohr atom. So this is a very good picture of a hydrogen atom with an electron in the lowest energy state. The electron occupies a cloud instead of an orbit, but it spends most of its time at the radius predicted as an orbit by the Bohr model. It also spends most of its time possessing the energy that an electron in that orbit would have. But of course, the atom is not always found in the lowest energy state, as there are other orbits allowed in Bohr's model. There are other higher energy states in the quantum mechanical hydrogen atom. These states are defined primarily by the quantum number n that we talked about earlier. And for each state, the electron has a different energy, which results from the shape of the electron cloud. For n equals 1, called the ground state, the shape is a symmetric cloud, the same in all directions. For n equals 2, the shape can take two forms, although both shapes have the same energy. One is a double spherical cloud, one sphere inside the other, while the other shape for n equals 2 is in the shape of a dumbbell. For other values of n, the shapes can be pretty strange,
Kind of like balloons or something.
like this torus, plus dumbbell shape.
I guess they're describing those balloon shapes as dumbbells. Yeah, because I remember, wasn't that P?
An electron in the lowest energy shell in an atom can be struck
I don't
by
remember all
and
the other
absorb
shapes
the energy
for the
of a
names
photon,
the, numbers.
giving
all
it
the shapes
enough
for the numbers
energy
of
to
the
jump to the
electron
next
clouds.
energy shell.
Anyways,
And the reverse process allows the electron to jump back down into the lowest energy shell and emit a photon. The color of the photon depends on the energy difference between the two shells. This explains the spectral lines that identify an element. Since white light contains all the colors in the spectrum, when we shine white light on a sample of an element under the right conditions, the atoms absorb all the photons that allow their electrons to jump to other energy shells. So, the absorption spectrum is all the colors in white light minus those that match the difference in energy shells within the atom. And when those electrons spontaneously jump back down to the lowest energy levels, that emission spectrum contains only the lines that match the difference in the energy shells within the atom.
Now it's time to investigate one of the most important properties of elementary particles. One that literally shapes the atoms of each element in the periodic table. Jeeves, please continue.
We have just discussed how Schrödinger's equation shows us how to accurately describe fundamental particles with a wave function. Now let's examine why two electrons together reveal a feature of quantum mechanics totally unlike anything in the large-scale world we inhabit. In a classical setting, even if two things are identical, they are still individuals. As long as we keep track of them carefully, we can treat them separately and label them A and B, or X and Y, or 1 and 2. But consider what is different about a two-electron system. Whether in an atom or in a box, it doesn't matter. Since the two electrons are consistently phasing in and out of existence, and since they are absolutely identical, it is impossible to keep track of specific individuals. Because of this, we must use a combined wave function to describe the pair rather than using two individual wave functions. This new two-particle wave function will have two parts to it, and those parts will either add or subtract. Physicists would say this makes the wave function either symmetric or antisymmetric. And it turns out that only the antisymmetric function works for the electrons, and quarks, and protons, and neutrons. Let's let this red wave represent the first part of the combined wave function, and this green wave represent the negative of the second part. If the electrons are in the same state, these two waves will be a mirror image of one another. As one goes up, the other goes down in perfect synchrony. So when we combine them, we get no wave at all. And since the wave is a map of electrons existing at that point, no wave means no electrons. So clearly, two electrons can never be in the same state, because that causes their combined wave function to disappear. Now, the only components making up the dynamical state in the atom is the shell it occupies, and another property that electrons have called spin. You can think of electrons as little spinning tops, if that helps. And these electron tops can spin in only two ways: upright or upside down, which can make them distinguishable. So the end result is that 2 and only 2 electrons can occupy each shell in an atom. One with spin up and the other with spin down. Other electrons in the atom must occupy higher and higher shells. This is called the Pauli exclusion principle, first espoused by Wolfgang Pauli. Without this exclusion, all electrons would occupy the lowest energy state, and atoms would behave very differently, and the universe would be a very different place. The fact is that the property called spin is quantized as well. No big surprise. And all the particles fall into one of two different families because of this. Those particles that have spin equal to 1/2, or 3/2, or 5/2, and so on, form the family called fermions. The name comes from Enrique Fermion, who along with Paul Dirac developed the statistical methods of dealing with them. Fermions are said to have half-integral spin. And as indicated above, electrons, quarks, protons, neutrons are all in this family. The other family of particles have spin equal to 0, 1, 2, 3, and so on. They are called bosons, after Satyendra Bose, who along with Einstein developed the statistics for dealing with this family. Unlike fermions, which must obey the Pauli exclusion principle, bosons do not. Groups of multiple bosons will all gather in the lowest available energy state. Photons, gluons, gravitons all fall into this family. If bosons had to obey the exclusion principle, many modern marvels could not exist. Like lasers, which require that huge numbers of photons be in the same state at the same time, and again, the universe would be a very different place.
Oh,
See.
day and night, but this is wondrous strange.
Yes, it is, Horatio. I mean, Diana. Quantum mechanics is different, but so far it isn't too weird. Okay, Jeeves, show us a little weird. Where
You just had to
is
say
the weird?
something, didn't you?
Where's the weird, you ask? Once you get past existence coming and going, and virtual particles, and uncertainty, and exclusion, most of the weird stuff in quantum physics comes from what is known as entanglement, and subsequently wave function collapse. When two or more particles interact, their wave function becomes entangled in such a way that some properties of each are now depending on what happens to the other particle. Then these particles can be carefully separated, while in careful isolation to distant locations. But as long as they're not disturbed, they are still entangled and still have properties dependent on each other. Then, when one particle is examined to see what the individual property might be, the wave function instantly disentangles. physicists would say this wave function collapses. Instantly, the other particle has its codependent properties disentangled and determined. Here is an example. We can set up a source to emit electrons in pairs, with their spins dependent on and opposite from one another. Now, neither electron knows what spin state it is in. Both are flip-flopping back and forth between spin up and spin down. But their wave functions are entangled, so that whenever one of the electrons is disturbed and settles into one of the spin states, say spin up, the other electron instantly settles into spin down state. And this instantly occurring collapse happens whether the electrons are next to each other or on the opposite side of the planet. And while some of that is truly weird, a host of modern technologies are beginning to rely heavily on this weirdness. Quantum computing, quantum cryptography, and quantum teleportation, to name a few. And because of the work they are doing in these fields and others, many scientists have little doubt that this particular quantum weirdness is an actual phenomenon. Real entanglement experiments have now been done where the separations have been over 100 kilometers, proving that distance does not destroy entanglement. This is analog. This is digital. This is analog. This is digital. This is analog. This is digital. If it is continuous, it is analog. If it is granular, it is digital. The current trend in audio, video, and communication technologies is to go digital. Instead of a continuum of color in video devices, we are limited to some finite number of colors. Instead of a continuous picture,
I forgot to
photo
chop the tree.
is divided into pixels.
I'm silly.
Instead of just any frequency in audio, we are limited to specific steps. This is very much like the universe in the realm of the small. The entire universe went digital about 14 billion years before we thought of it. Space, time, energy, momentum are all granular. There are only certain specific values allowed, and this granularity is accurately described by quantum mechanics.
Okay, so this little thing is a credit sequence, and this entire video is a chain of separate episodes. Alright, I see.
Carbon is a critical ingredient for life on Earth. All living things are made up of about 25% carbon. The carbon atom is unique because it can bind to other carbon atoms to form long chains and rings. and these in turn serve as the backbone of complex molecules that make life possible. The nucleus of a typical carbon atom has 6 protons and 6 neutrons. But about 1 carbon atom out of every 100 has 1 extra neutron. This has very little effect on the properties of the carbon other than making it slightly heavier. Chemically, it acts just like any other carbon atom. It is called carbon-13. And there's an even rarer type of carbon. It is formed high in the atmosphere when cosmic rays strike atoms of nitrogen, converting them into carbon-14. Carbon-14 is also chemically identical to regular carbon, but the nucleus of carbon-14 is unstable. After some amount of time, which could range from a few days to many thousands of years, carbon-14 decays back into nitrogen. But since carbon-14 is formed at a steady rate, there is a constant level of it in the environment. Out of every trillion carbon atoms in your body, only 1 dozen of them are carbon-14. As long as an organism is alive and eating, it maintains a constant ratio of carbon-14 to regular carbon. But once the organism dies, the amount of carbon-14 in the body begins to decrease. After 5,000 years, about half of the original number of carbon-14 atoms will have decayed. Using this fact, scientists can tell how long ago an organism died.
So we're going to explain carbon dating in this episode.
Consider the Earth and a rocket ship which are bound together by gravity. If it takes work or energy to pull them apart, then the binding energy is the amount of energy it takes to completely separate them. Similarly, the binding energy in a nucleus is the amount of energy it takes to completely separate the protons and neutrons, collectively called nucleons. There are 2 forces acting inside the nucleus of atoms. The nuclear force, a residuum of the strong force that holds quarks together, is pulling the neutrons and the protons together, and the electric charge on the protons is pushing them apart. The strong force is a lot stronger than the electric force at short ranges, up to 2.5 times the proton diameter. But at larger distances, the electric force dominates. So as we add nucleons and work our way up the chart of the periodic table, initially each nucleus is generally a little more tightly bound than the one before. This chart gives the actual numbers. This increase in binding energy continues until we get to iron and nickel, where the nucleus has about 60 nucleons in it. At this point, the nucleus has a radius more than 2.5 nucleons wide, which you remember is the range at which the repulsive electromagnetic force begins to dominate. So as we add nucleons past this point, the electric force trying to tear the nucleus apart starts winning, and each added nucleon is a little less tightly bound. When we get to lead and bismuth, and the nucleus contains 207 nucleons, the electric force wins, and the atomic nuclei larger than this are unstable and come apart by themselves, although it may take a while. These larger nuclei can return to more stable arrangements in several ways. They can convert neutrons into protons and give off beta radiation, or kick out whole groups of nucleons, 4 at a time, in alpha radiation. Or they can simply split into other smaller, more stable nuclei. When this happens, we call it fission. Fission is different from the other forms of decay because it can be harnessed and controlled via chain reaction. Now let's consider what this means from an energy perspective. According to the binding energy chart, uranium has 7.6 MeV of binding energy for each nucleon, for a total of 1,786 MeV. while barium-144 has 8.3, and krypton-89 has 8.8. And the extra neutrons have no binding energy. So every time a nucleus of uranium fissions, we get about 192 MeV of energy. But U-235, left to its own devices, might take billions of years to decay. So we will want to help it along. We do this by shooting a slow neutron into it. It absorbs the neutron and briefly becomes U-236. Then it splits into krypton-92 and barium-141. And three
We're just going to
neutrons.
explain all sorts of radiation.
Those three neutrons
radioactivity
go to split other U-235 atoms into other daughters of more neutrons, and the process grows and repeats again. We can put the whole thing in water, and the daughter fragments and neutrons will be slowed by the water and cause it to heat up. Finally, we can use the steam to make electricity. This is how a nuclear power plant works. Ever since Einstein demonstrated the equivalence of mass and energy, physicists often give the rest mass of tiny particles like protons, neutrons, and electrons in units of energy. Two convenient energy units are the electron volt, or eV, and its cousin, million electron volts, or MeV. Using these units, here are some facts that will come in handy. The rest mass of the proton is 938.272 MeV. The rest mass of the neutron is 939.566 MeV. Let's take another look at the chart of binding energy of atomic nuclei. And now let's talk about fusion. If we can take a nuclei of deuterium, which has one proton and one neutron in its nucleus, and get it to fuse with a tritium nucleus, which has one proton and two neutrons, we would end up with helium, one extra neutron, and some energy. And we would have the basis for an energy-making machine. Let's run the numbers and see how it works. The binding energy for deuterium is about 2 MeV. And the binding energy for tritium is about 8 MeV. So the total for the input items is 10 MeV. The binding energy for helium is 28 MeV, and the free neutron has 0 binding energy. Subtracting the 10 MeV from the 28 MeV reveals that every time this fusion happens, we liberate 18 MeV of energy. And that's pretty good. But there's a problem. Getting the protons in the deuterium and the tritium close enough together so the nuclear force fuses them together is hard to do on Earth. This is the energy that powers the sun and the stars. But the sun's gravity holds the fuel in place, while the high temperature gives the nuclei enough speed to overcome the electric repulsion. If we could make a miniature star in the lab, a microsun, then we would be well on our way to having a great solution to our energy problems. And although this has proven difficult, significant progress continues to be made. Similar to tritium is an isotope of helium called helium-3. It could be substituted in the above reaction and would produce a similar amount of energy. What's the difference? Well, there's an estimated 1 million tons of easily mined helium-3 on the moon's surface. It would only take 25 tons to satisfy all the energy needs of the United States for an entire year. And 25 tons also happens to be the maximum payload of the space shuttle. And now you know why we're going back to the moon.
Gonna be powered by moon rocks.
Why is gravity so weak? Why can a small magnet pull or push something away from the entire Earth? There is an idea that may explain it. But before we go there, let's explore more preliminary ideas first. The most popular quantum gravity theory of today describes all fundamental particles as vibrating strings of energy.
Let's
And
not
the
do
theory is constructed
string
in a
theory,
whopping
please.
9 or 10 spatial dimensions instead of the 3 that we experience in our everyday lives. But what is a dimension? A line is a familiar geometric figure and can be completely described by giving its length. It is a one-dimensional object. It can be imagined that the dimensionality of an object can be created by taking an object of one less dimensions and moving it at a right angle to that dimension. You can create a line in your imagination by thinking of taking a point and moving it. Next, consider a surface. A surface is also quite familiar. A surface has both length and width and requires 2 measurements to define it, and therefore is a 2-dimensional object. Similar to a generation of a line from a point, we can generate a 2-dimensional surface by taking a line and moving it in a direction other than the direction of the length. And a solid figure is the stuff of everyday life. It has length and width and depth, and requires 3 measurements to describe it, and is a 3-dimensional object. And like the generation of a surface from a line, we can generate a 3-dimensional object like a cube by taking a square and moving it in a direction other than the direction of the length and the width. Cylinders, cubes, and spheres are 3-dimensional objects. And now the hard part. The higher dimensions are created by moving a 3-dimensional solid in a direction other than the length, width, or height. And while that is easy to do mathematically, it is impossible for us to picture it. So let's examine how we might detect these other dimensions. We begin with bright light spreading out in a spherical shell. The intensity of the light at any one point will fall off the square of the distance from the source, because the surface that the light covers grows as the square of the distance from the source. But that is only true in 3-dimensional space. In 4-dimensional space, the light will grow dimmer as the cube of the distance. And in 5 dimensions, it will grow dimmer as the 4th power of the distance. And in 10 dimensions, it will grow dimmer as the 9th power of the distance. Now back to strings. If this membrane represents the 3 dimensions that we live in, then particles like quarks and electrons are the strings that have the endpoints forever attached to those 3 dimensions. They might look like this. But the particle that is the force carrier for gravity, the graviton, is a closed loop. It has no ends that are constrained to our 3 dimensions. So if there are other dimensions, gravity will propagate freely there as well as in our familiar 3. And that might explain why gravity seems so weak to us. We experience only a tiny fraction of gravity's true strength because so much of it is leaking out into other dimensions.
You've conflated 2 different definitions
But
of
where are
dimension.
these dimensions hiding?
Come on now.
One possibility, but not the only one,
Not consistent with
is that they're all around us, but incredibly tiny.
space versus measurement.
If you
I
look
should
at a
say.
wire or a string from far enough away, it looks like a line, a one-dimensional figure. But if you get closer, or if you were a lot smaller than the thickness of the wire, then you would easily see that it has other dimensions. On the tiniest of scales, space has extra dimensions at every point. It might look something like this if we were small enough to see it. Accelerators like the LHC at CERN smash protons against antiprotons at enormous energies, perhaps enormous enough to produce gravitons. And if they do, then perhaps we might just be able to see them form in our limited three-dimensional world and slip quickly and quietly away into those hidden dimensions.
We now examine a phenomenon which is absolutely impossible to explain in any classical way, and which is at the very heart of quantum mechanics: the famous double-slit experiment. To understand this experiment, we first need to see how ordinary particles, or little balls of matter, act. If we shoot small objects, such as marbles, at a screen containing a single slit, we see a pattern form where they went through the slit and hit on the back wall. Now, if we add a second slit, we would expect to see two bands directly behind the slits. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we shoot particles such as matter through two slits, we get this: two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marbles, a single band. So, if we shoot these tiny particles through two slits, we should get, like the marbles, two bands. What? An interference pattern? We fired electrons, tiny bits of matter through, but we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off of each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither, and it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So, they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. This led to many questions. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? It was as if the electron decided to act differently, as though it was aware it was being watched. It seemed as if the observer somehow collapsed the wave function simply by observing. However, physicists eventually realized that any type of measuring device, no matter how small, always interacted with the electron, subsequently destroying the interference pattern. Werner Heisenberg proposed a new uncertainty principle describing this. The uncertainty principle can be stated in terms of our experiment as follows. It is impossible to design an apparatus to determine which slit the electron passes through that will not at the same time disturb the electron enough to collapse its wave function, destroying the interference pattern. And it was here that physicists stepped forever into the strange netherworld of quantum uncertainty.
What is the temperature of outer space? Way out there, between galaxies, where there is only one hydrogen atom per cubic meter. Can an individual atom be hot or cold? Can it even have a temperature? It sounds a little silly to say an atom is 27 degrees Fahrenheit or something. But temperature really is a measure of the motion energy of an atom. If an atom is motionless, then it is at 0 Kelvin. We don't say degrees Kelvin anymore. Now, it can never be really motionless, so it can never be at exactly 0 Kelvin. And it moves pretty fast as temperatures rise. At a tiny fraction of a degree above absolute zero, the atom is already moving at about 1 centimeter per second. For subatomic particles, the energy is often measured in MeV or GeV. An electron with 1 GeV of energy is moving close to the speed of light. And that corresponds to a temperature of 11,000 billion Kelvin. For a collection of atoms or molecules like a gas or a crystal lattice, the temperature of the collection is just an average temperature of the group. But of course, because of collisions and interactions at the molecular level, a group of atoms or molecules will distribute the total motion energy pretty evenly among the individuals in the collection. And if two or more systems are brought together, some motion energies from the hotter system will flow to the colder system until they are both at the same temperature. When you measure your body temperature using a thermometer, your body cools down a tiny bit, and the thermometer heats up until the two are at the same temperature. Then reading the thermometer's temperature also reveals your body temperature since the two are the same. If we take a quantity of gas and enclose it in a container, the individual molecules in the gas consistently bang into the walls of the container, creating a pressure on the walls. We can do 3 different things to increase the number of wall collisions. Increase the number of atoms in the container by adding more gas. Or increase the motion energy of the atoms already in the container by heating the gas. This makes them go faster and increases the number of times that each atom hits the wall. Or we can make the container smaller, decrease the volume, so that the individual atoms have shorter distances to go to collide with the wall. This leads directly to the ideal gas law, relating temperature volume, pressure, and quantity of gas. Snuck that one in on you, didn't we? It all started with light, smart light. Then it quickly spread to rocks and other projectiles. Now it's seemingly everywhere. But before I tell you about that, consider how smart people react to certain situations. If I have a trial where you have to start at point A and run and touch any point on the wall, and then run to point B,
Fucking good
how
enough.
do you decide what is the quickest path to take? And how do you decide where to touch the wall? You could run to here, or here, or here. But after a moment, you pick this point because you think it's the shortest path and results in the quickest journey. In a second trial, you are a lifeguard and you spot a swimmer in trouble out in the water. How do you decide the quickest path to the swimmer? You run faster than you can swim. So do you run to this point and swim from there? Or maybe this point? If you choose correctly, your path will be the path of minimum time, and you will have joined the ranks with Fermat, Maupertuis, Euler, and Lagrange in furthering one of the most universal principles of nature. Living in the first half of the 17th century, Pierre Fermat developed the concept that light travels at different speeds in different media, and maintained
It's
that the
Fermat
path
for
the
the-
light takes is always the
for the
one that
record.
takes the least time. His detractors at the time gleefully pointed out the obvious objection. How does the light know which path will be the quickest? Smart light? Pierre-Louis de Maupertuis, the son of a wealthy pirate, expanded Fermat's least time idea. He wrote that in all events in nature, there is a certain quantity called action, which is always a minimum. His good friend and mathematician, Leonard Euler, added the idea of conservation of energy and made least action an exact dynamical theorem with this mathematical form. Euler also developed an ingenious graphical method to find the path of minimum action for a system. Another young scientist of the time, Joseph Louis Lagrange, eagerly applied these ideas to the Tantochrome problem. This is the problem of finding a curved shape on which a weight started at any point on the curve will slide to the bottom in the same amount of time regardless of its starting point on the curve. He expanded the idea of action to be the function of kinetic energy minus the potential energy. This is proven to be a much more universal formulation. Now that we know all of this, let's throw a small baseball straight up with enough force that it returns to our outstretched hand 3 seconds later. And let's see if we can discover its motion using the principle of least action. When we first throw it, it has a lot of kinetic energy, and its speed is at a maximum. But gravity slows it down as it rises. At its peak, its speed is 0, and all of its energy has been transformed to potential energy. On the downward trip, all the potential energy gets reconverted into kinetic energy. Its kinetic energy is related to its speed, and its potential energy is related to its height. Now on this graph, we have the baseball's height on the y-axis and the time on the horizontal axis. To begin, we have divided the 3 seconds of flight time into a few time intervals. As we adjust the height of each point, the computer will calculate the total actions for us. Remember, we're looking at the minimum actions possible while keeping the ball in the air for 3 seconds. The height of the dot is directly related to the potential energy, and the slope of the line gives the speed, which is related to the kinetic energy. The steeper the slope, the faster the baseball is moving. As you can see, it is an iterative process. It will take several cycles before we can no longer make the total actions any lower. That is, less negative. Here's the same problem with more sections in the graph. To do this perfectly, the number of sections must go toward infinity, and the width of each section must go towards 0. But this approximation with 40 sections is good enough to show all the features. Now that we have the motion, let's examine the path, or world line, and see what we can see about how smart that baseball really is. The numbers to the right list the change in velocity for each segment, as well as the acceleration for each segment. You can see that the change in velocity is constant from section to section, and the acceleration is equal to the standard value for the acceleration of gravity, 9.8 meters per second squared. Since we are on a roll, let's do it one more time, showing for each section the kinetic energy, the potential energy, the difference between the two, as well as the total energy. Adding the t minus v column gives the total action, which is smaller on the path than any other possible path. You can also see that the total energy is constant, as it must be if energy is conserved. And to demonstrate how versatile this baseball is, let's throw it onto the roof of a house, so the endpoint is 4 meters higher than the initial point. Method still works pretty well. Smart baseball. While everyone has heard of Isaac Newton, and force equals mass times acceleration, it is this other equivalent formulation of kinematics that is more versatile and has direct extensions into relativity and quantum mechanics. So, how does the light know which path to take to satisfy the principle of least action? Richard Feynman gave us the answer, and we will explore that answer in another video on QED. This is a photomultiplier. It counts individual photons. This is one easy way that we know photons are particles. If light wasn't made up of particles, we couldn't count them. Every instrument that has ever been designed to detect weak light has shown the same thing. Light is made up of particles. Today we are going to examine how light interacts with matter. And all you need to know about light to follow along are the familiar everyday properties of light. Like light goes in a straight line. It bends when it goes into water. When it reflects off a mirror, the angle at which it hits the mirror is equal to the angle at which it leaves the mirror. Light can be separated into colors. You can see beautiful colors on a puddle if there's a little bit of oil on it. A lens focuses light, and so on. Almost everyone has experienced looking out a window and seeing themselves partly reflected in the glass. Let me tell you about an experiment in which photons of just one color, say red, are emitted from a light source down towards a block of glass. A photomultiplier is placed at point A above the glass to catch any photons that are reflected from the front surface. And another photomultiplier is placed at point B inside the glass. And we find that on average, every 100 photons that we shine straight down on the glass, only 4 arrive back at A, while 96 arrive at B. But now we have a real problem. If we think about each photon encountering the glass, we might wonder, how does a photon decide whether to go through the glass or reflect back into the room? Okay, let's do it again. Only this time, we replace the block of glass with a thin sheet of glass, and we move photomultiplier B to the other side. Now the photons can reflect off either the front or the back surface of the glass in order to show up at A. We might expect that 4% would reflect off the front surface and 4% of the remaining photons to reflect off the back, making a total of about 8%. But what we find is that with some sheets of glass, 15 or 16 photons find their way back to A, and with other sheets of glass, we get only 1 or 2. Some sheets of glass reflect 10%, and others eliminate particle reflections altogether. After checking the glass sheets very carefully, we find they differ in only one respect. They vary ever so slightly in thickness. With this as a clue, we redo the experiment with progressively thicker and thicker glass. And sure enough, we see the particle reflection vary from 0 to 16%, and back to 0, and back to 16%, and back to 0 in a continuous cycle. Wow, how can that happen? How can adding a second surface somehow turn off the reflection from the front surface? How does the photon know how many surfaces it will encounter before it gets to them? The answer is that each photon travels every possible path simultaneously. There's no decision making at all. And the probability of each final outcome is determined by adding the probability from each possible path. And each individual path probability can be represented by a little arrow, such that the actual probability is the square of the length of the arrow. For example, in the first experiment, we found that the probability that the photon would arrive at photomultiplier A was 4%. That corresponds to an arrow whose length is 0.2, because 0.2 squared is 0.04. In the second experiment, there are 2 paths for the photon to get to A. So there must be 2 arrows, and we must add them. But how do we add arrows? We simply put the tail of the second arrow at the head of the first and draw a new arrow from the tail of the first to the head of the second. Now, to determine the direction that each arrow points, imagine that there is a stopwatch that times the movement of the photons along a path. When the photon leaves the source, we can start the stopwatch. And when the photon triggers the photomultiplier, we can stop the stopwatch. And whatever direction the hand points is the direction of the arrow for that path. Except we need one more rule. When the path includes reflection off the front surface of the glass, we reverse the direction of the arrow. Let's draw the arrows from the case of light reflecting from a very thin plate of glass. For the front reflection arrow, we start the stopwatch when the photon leaves the emitter. It bounces off the front surface and enters the photomultiplier, and we stop the stopwatch. Then we draw a little arrow of length 0.2 in the direction opposite that of the stopwatch hand. For the back surface reflection arrow, we repeat the procedure. And when the photon arrives at the photomultiplier, we see that the stopwatch hand is pointed in almost the same direction as for the other path. Because the glass is so thin, the back reflection path is about the same length as the first, and the stopwatch hand has turned only a tiny bit more. So we draw a little arrow of length 0.2 in the same direction that the stopwatch is pointing. Now let's combine the arrows. Since they are nearly the same length but point in the opposite directions, the final arrow has a length of nearly 0, and its square is even closer to 0. So the probability of light being reflected from a really thin layer of glass is essentially 0. As we replace the glass with increasingly thicker pieces, we can see that the stopwatch for the second path would turn more and more as the path gets longer. So the resultant arrow gets longer and longer as well, and the probability of reflection grows. When the glass is just thick enough for the stopwatch to make a half turn, the length of the two arrows add to give us 0.4. And the probability of reflection is the square of this, or 16%. As the glass keeps getting thicker until the stopwatch has made a complete extra turn, the resultant arrow is back to 0, and the probability of reflection is back to 0, and the cycle starts again. If we repeat this experiment with other colors of light, we would get similar results. Depending on the thickness of the layer of glass, we would get repeating cycles of reflection probabilities ranging from 0% to 16% and back to 0. But with one difference. The stopwatch hand turns at different speeds for each different color of light. So the thickness of the glass that results in 0% or 16% reflection is different for each color. And that explains the colors we see when the light is reflected from a thin film of oil on a mud puddle. The oil film is never exactly uniform in thickness, so different sections of the film are just the right thickness for reflecting red light, or blue or green light. So we see the entire rainbow of colors reflected from different areas of the film. Now let's replace the glass with a mirror. We move the light source off to one side and move the photomultiplier off to the other side. And let's add a screen in the middle so the photons can't go straight from the source to the photomultiplier, but we have to reflect off the mirror. Now our experience suggests to us that the photons will bounce off the center of the mirror because that's where the angle of incidence is equal to the angle of reflection. And our intuition makes it seem obvious that the parts of the mirror out to the ends don't have much to do with it. But that would take us back to the concept of smart light. How does the light know that it's supposed to travel in a single path? So let's examine how our idea that light travels every path can give us the right answer. Start with the fact that light has equal probability of reflecting off the mirror at every point. So when we draw our arrows, they will all have the same length. And let's simplify the situation by first looking at the 15 representative paths. These paths. Now, as we said before, the length of the arrow for every path is the same length, but we still need to calculate the direction for each arrow. And remember that the direction is determined by how much the stopwatch has turned during the photon's trip. The paths out near the ends of the mirror are the longest. Not only that, the change in length from path to path is greatest out near the ends as well. So the adjacent arrows will turn a lot from path to path. The first four will look something like this. As we get closer to the middle, the paths get shorter, and the difference in path length from path to path is much smaller. So the arrow turns a lot less for adjacent paths. The next 7 arrows look something like this. And the arrows for the paths at the right end are just like the arrows for the similar paths at the left end. Now let's join the arrows head to tail and draw the final arrow. And what do we see? First, the ends of the mirror are not important because the times are different from path to path. The arrows from the first part just go in a spiral. If we chopped off the ends of the mirror, it wouldn't change the end result very much. And the paths near the center contribute most to the final arrow. This is where the time of travel is the least. This is where the angle of incident equals the angle of reflection. And that is why you can get away with saying that light only reflects off the single point in the middle, even though that it's wrong.
That's the most
Let's test the idea that reflection is really happening all over the mirror. Let's remove the parts of the mirror in the middle and on the right, leaving only this portion on the left. And now let's force the arrows on the left to point in pretty much the same direction instead of pointing all over the place. We do this by noting how fast the stopwatch is turning, and by scraping away all the portions of the mirror that would give arrows that point to the left. Now when we add our arrows, we get a final arrow of substantial length. So we should get a strong reflection from our off to the side scraped up mirror. Does this really happen? Yes, it does. This type of mirror is called a diffraction grating, and it works like a charm. And since the stopwatch spins at different rates for different colors, the spacing in diffraction grating changes from different colors of light. But instead of actually changing the spacing, we can just move the photo multiplier up and down a bit. Changing the angle achieves the same end as changing the spacing. This is why a series of grooves, like on a music CD, reflect different colors of light at different angles. So a grating shows that light really reflects from all parts of the mirror, and light isn't so smart after all. We could continue describing interference and
So
other
every path is in
phenomena
competition
with our
with each
every
other,
path
and,
method and spinning arrows.
only the most
But
prevalent
suffice
wins
to say,
that
the
competition.
method
Or
works.
the most, yeah,
Always
prevalent,
works.
right? Relevant.
Exactly works.
The most important, the most
So
magnificent.
let's turn
the
our
best.
attention to the interaction of light and electrons.
It's the free
We
market
can
at
apply
work
the every
with
path
photons.
method here as well. We start by drawing diagrams of every possible path for an interaction to occur. And surprisingly, we can reduce the task of making these diagrams to just 3 fundamental actions that we need consider. Every possible interaction diagram can be reduced to combinations of these 3. 1. A photon goes from place to place. 2. An electron goes from place to place. 3. An electron emits or absorbs a photon. Each of these basic actions has an amplitude, an arrow, that can be calculated according to certain rules. Let's draw a diagram of one action. A photon goes from place to place. We put time on the vertical axis and space on the horizontal axis, and we will represent the photon by a wiggly line. So basic action 1 looks like this. There is a certain probability amplitude for the photon to go from A to B. Let's call it P, A to B. And there is a formula for the size of the corresponding arrow. In the second basic action, an electron goes from point A to point B. let's call the amplitude for this action E, A to B. Notice electrons are represented as straight lines. The formula for the amplitude of this action includes a very special number called n. And it's interesting to note that the formula for P, A to B, a photon going from point A to point B, is the same as E, A to B, an electron going from point A to point B, if n is set to 0. The third basic action is an electron admits or absorbs a photon. This action is called a coupling. Every coupling is a junction between two straight lines and a wavy line. There's no complicated formula for the amplitude of coupling. It is just a number, and we call it J. Its value is about negative 0.1. Now let's calculate the probability that two electrons at 2 points, 1 and 2, end up at points 3 and 4. This event could happen in two ways. The electron at point 1 could go to 3, given an amplitude of E 1 to 3, and the electron at 2 goes to 4, giving E 2 to 4. So the overall amplitude for this path is E 1 to 3 times E 2 to 4. Another way would have electron 1 go to 4 and electron 2 go to 3. This would have an amplitude of E 1 to 4 times E 2 to 3. And of course, the final step is to add these two arrows to get the total amplitude. This would be a good first approximation, but we should also consider other ways this event could happen. For each of the ways we just described, one electron could emit a photon on the way, and the other electron could absorb a photon along the way. Calculating this complicated amplitude involves the number J we mentioned earlier. It is shown here. And there are more possibilities. This looks hopeless, but the number J will come to our rescue. The first ways this event could happen have no J's in the calculation. The next way had J times J. And the last would have J times J times J times J. And since J times J is less than 0.01, the arrow from this possibility is only 1% as long as the arrow for the first way. And the J times J times J times J path is less than 1/10,000th as long as the no J method. So you only have to go to the more complicated possibilities if you need increased accuracy. When an electron is placed in an external magnetic field, it exhibits a response called its magnetic moment. The diagram for the first approximation of the magnetic moment of an electron is very simple. An electron goes from place to place and couples with a photon from a magnet. This gives a value of 1 for the magnetic moment. After some years, it was discovered that the value was not exactly 1, but something like 1.00116. In 1948, the first second-order corrections were made. They involved J times J terms from diagrams like this. To calculate the contributions from this class of diagrams, we had to make an arrow for every place in space-time that the photon could be emitted and every place that it could be absorbed. And since then, experiments have measured the magnetic moment to even greater accuracy. So now we needed to consider all the ways the electron can go from place to place with 4 extra couplings. It took 2 groups of physicists 2 years to calculate these terms. The term with 6 extra J's involves even more possible ways the event could happen. It took 20 more years to get this extra accuracy figured into the theoretical value of the magnetic moment. With better computers, more and more J's have been added. And theory and experiment now agree in more than 16 decimal places. If this accuracy was matched in measuring the distance from the Earth to the Moon, we would know the lunar distance to an accuracy smaller than the thickness of a single human hair. Quantum electrodynamics is perhaps the single most successful physical theory ever devised. It forms the bedrock foundations for all of today's unification theories, like the Standard Model. QED, quod erat demonstrandum.
Guess we're up to the last episode now.
Diana, did you ever stop to be amazed at how a GPS unit works?
Not really. I got one for my birthday once. Chaucer, did you ever use one?
No, never needed one myself. I always know where I've been, so I always know where I am. Kevin, are you going to tell us how it works?
I sure am. It's a good intro into relativity. Jeeves, want to take over?
Oh, Chaucer, you do it. All of it.
Relativity
Jeeves
is just
has
a
done
method
enough.
for two people to agree on what they see if one of them is moving. And since we all move about pretty regularly, we can find many examples of how useful relativity is in everyday life, even if we don't call it by name. One miracle of modern life is the Global Positioning System, or GPS. It is pretty amazing that the GPS can pinpoint your location anywhere on Earth to within a few yards. And this magic depends entirely on the existence of 24 satellites 12,000 miles above the Earth, and a little relativity. Briefly, here's how it works. The GPS receiver gets a timing signal from several different high-flying satellites, and using Einstein's theory of relativity, it calculates the distance from each satellite. Throw in a little triangulation, and out comes your location. Simple in concept. But to do this successfully, the timing signals must be accurate to a few billionths of a second, so that the distance
Forgot to finish
calculations
that other wall
can be
with one
accurate
stick.
to a few yards. But with all this motion going on, time and distance must be reconciled carefully. Without Einstein's version of relativity, the accuracy of the global positioning system would drift more than 7 miles every day. But of course, relativity was not a new concept with Einstein. The problem of how two people reconcile their observations about the world if one of them is moving has been addressed for centuries. Let's ease our way into relativity with some common experiences. If you are traveling in a car on a smooth, straight stretch of highway, there's no sensation of motion at all.
You mean I could read a book, pour a drink, flip a coin, and everything looks and feels the same as if the car were sitting still?
That's because relative to the car, you, the book, the drink, and the coin are not moving. Notice that this works only if the car is not changing direction or speed.
So if the car accelerates or turns, pouring that drink becomes a real problem. Oh, but constant motion feels just like sitting still.
And if you want to know what it feels like to move at 1,000 miles per hour, just look around. Because of the Earth's spin, we zip along our time zone at a speedy 1,000 miles per hour. And because of its motion around the sun, the Earth carries us through space about 67,000 miles per hour. And because of the motion of our solar system, about the center of our galaxy, we are moving at more than 500,000 miles an hour. But it's not enough to ask, how fast am I moving? We must ask, how fast am I moving relative to some other thing? Let's make up a simple rule that allows two observers to agree on how fast something is moving. We begin at a moving walkway at the airport. The walkway is moving at a brisk 3 miles per hour. So, if Susan simply stands on the walkway, she is moving at 3 miles per hour, relative to Sarah, who is standing still but not on the walkway. If Susan walks on the walkway at 3 miles per hour, she can accurately say she is walking at 3 miles per hour. But Sarah sees her moving at 6 miles per hour. And if Susan walks against the walkway at 3 miles per hour, Susan can still say she's walking at 3 miles per hour. But now Sarah sees her as standing still, 0 miles per hour. So our first conclusion is that two observers can simply add or subtract their speed with respect to each other to any measurement of velocity they make. This idea is the basis of classical relativity. Here's another scenario. Suppose there's a truck moving down the road at a constant speed of 50 miles per hour. On the back are a baseball pitcher, a catcher, and their pitching coach, armed with a speed gun. As long as the truck doesn't speed up or slow down or hit any large bumps, they can conduct pitching practice just the same as they would on the baseball field. And when the pitcher throws a 100 mile per hour fastball, the coach's speed gun will read 100 miles per hour.
And now I remember why I wanted to go back there.
The ball is
Okay, let's
indeed
do
moving 100 miles per hour relative to the pitcher, the catcher, the coach, and the truck. But suppose an observer standing by the side of the road clocks the speed of that same baseball. What speed would this observer measure for the ball? Well, the ball would already be moving at 50 miles per hour when the pitcher was just holding it. So this observer would measure a speed of 150 miles per hour for the pitch. The speed of the ball relative to the truck, plus the speed of the truck relative to the observer.
This seems pretty easy. Early scientists just needed to visit an airport or play baseball on the back of a truck, and they became absolute relativists.
Yep, but not many of them took advantage of those opportunities. Kyrie eleison. Well, let's start our examination of relativity and light with a flashback teaser. Imagine you and Sky King are flying in the Songbird, and you have a Red Ryder BB gun with you. You know that you're flying at 150 miles per hour, and you also know that when you fire your rifle at the target range, the bullet leaves the muzzle at only 100 miles per hour. So the plane flies faster than the bullet. Now you point the rifle in the same direction that you're flying and pull the trigger. What happens? Does the bullet ever leave the muzzle? Since you're flying at 150 miles per hour and the bullet only travels at 100?
A fun question, but an easy one. Sure it does. The bullet's speed from the rifle gets added to the plane's speed, and the bullet takes off at 250 miles per hour. Reason it out this way. The bullet is moving at 150 miles per hour just sitting in the gun.
I don't want to use the word
evolve. You and Sky
There's no
King
such thing as
and
devolution.
The then when you
we've
fire
gone
the gun,
from
the bullet
quantum
is
mechanics
blasted
to
forward at an additional
physics
100 miles
101.
per hour. So it leaves the muzzle at 250 miles per hour relative
But I guess
to
it's
the
just
ground.
teaching you how to
100 miles per hour
so that you
relative
can
to you,
figure
Sky
out how
King,
quantum
and
mechanics
Songbird.
relate to
This is classical relativity. Simply
all
add
the
the
earlier
velocities.
concepts.
Okay, but now suppose you're with Snoopy
Maybe,
in
maybe.
his Sopwith Camel, and you know that on the ground, light from your flashlight travels at
Whatever, we'll see.
186,000
We'll
miles
see.
per
No
second.
conclusions.
Now from the plane, you point the flashlight forward and turn on the beam. Does the light travel forward at 186,000 miles per second plus the speed of the plane?
I know the answer, but I don't understand it. If that's what you're going to talk about today, I can't wait. Preach away, my hero.
Okay, here we go. Jeeves?
The example of adding velocities, in the bullet and plane example, is classical relativity at its finest. This classical version of relativity, simply adding the velocities, worked perfectly well for centuries for describing horse carts and ships, or baseballs and trucks, even airplanes, and rockets and bullets. But the relativity of classical physics is merely a very close approximation to reality. At very, very fast speeds, classical relativity breaks down. But this wouldn't be clear until scientists began flying Sopwith camels and examining the nature of the fastest known thing, light. In the middle of the 19th century, it had been known for quite some time that electricity could be used to make a magnet, and that magnets could be used to make electricity. But the man who made the first color photograph, James Clerk Maxwell, unified everything known about electricity and magnetism in 4 magnificent equations. And these equations described an electromagnetic wave that would travel through the empty space at exactly the measured speed of light. And in fact, this wave was light. According to Maxwell, light was an electromagnetic wave that moved through empty space with a speed of 186,000 miles per second. But from the standpoint of relativity, the question naturally arises, relative to what? The equation seemed to say that light moved at 186,000 miles per second, relative to everything. This was a dilemma facing the physicists at the turn of the 20th century. If Maxwell was right, then light moves with a velocity of c. 186,000 miles per second, always. But if classical relativity was right, there is no absolute velocities. And the velocity of light should depend on who is doing the measuring and their motion relative to the source of the light. How could both be right? Either our understanding of motion or our understanding of electromagnetism and light were in jeopardy. The very foundation of physics was facing a crisis. A 26-year-old patent clerk named Albert Einstein would provide the way out of this crisis. Einstein accepted both of these seemingly contradictory notions and changed the course of science. He accepted the idea of relative motion, but restated it as follows. Any person moving at a constant velocity will observe the same laws of physics that a stationary person observes. And since the speed of light is part of the laws of physics, Einstein postulated that all observers will measure the same speed of light, regardless of their state of motion. But speed is just a measure of distance moved in a given time. And in order to agree on the speed of light, different observers might have to disagree about distance and time.
Okay, I think I'm getting it. If we have to agree on velocity, then we might have to disagree on the components of velocity?
Absolutely true.
You may have heard the term light year, used in astronomy or cosmology. A light year is the distance that light travels in 1 year, about 6 trillion miles. So you could say that the speed of light is 1 light year, a distance, per year, a measure of time. You could just as easily say a light second is the distance that light travels in 1 second, about 186,000 miles. And so the speed of light is 1 light second, a distance, per second, a measure of time. Here are 2 starships, one at rest and the other in motion. When the moving ship passes the stationary ship, each fires its laser. Now, according to Einstein, the speed of the laser light doesn't depend on the motion of the ship. So we see both beams traveling side by side at the same speed. The crew of the ship at rest witnessed their laser beam traveling 12 light seconds in 12 seconds, and report that light travels at the speed of 1 light second per second. Correct. But what about the beam from the moving ship? Does it travel only 6 light seconds in 12 seconds? If so, the crew on board the moving vessel would report that light travels at only half speed? No, they wouldn't. But why not? According to Einstein, light always travels at 1 light second per second, regardless of the motion of the person who measures it. How do we fix our picture so that this is right? Part of the answer lies in the fact that the clocks on the moving ship slow down. As we stated earlier, if we must agree on the speed of light, we may have to disagree on the measure of time. If the clocks on board the moving vessel ran only half as fast as the ones at rest, our problem would be completely solved. The light beam from the moving ship would still travel 6 light seconds, and with the slow clocks, it would take only 6 seconds for this to happen. And the crew would report that light travels at precisely 1 light second per second.
Well, who cares?
But it turns out the clocks don't slow down enough to be the whole answer. So in a minute, we'll look at the second part of the answer.
And of course, this isn't a statement about clocks. It is time itself that slows down. Right? Over the last 100 years, countless experiments have shown without a doubt that it is time itself that slows down. But why does it occur? Jeeves, please.
A clock is any device that counts events that occur at regular intervals. The event that drives a clock can be just about anything. The swing of a pendulum, the bounce of a ball, the unwinding of a spring, or the changing current in an electric circuit. Any regular event will do. Let's imagine constructing a clock in which a beam of light bounces between two mirrors. Whenever the light strikes the bottom plate, the clock advances. The advantage of using this kind of clock is that we can be sure that the observer who looks at the clock will see the timing mechanism, the beam of light, moving at the same speed. If two such clocks are stationary, then we would expect the time indicated on each clock to be precisely the same. But what happens when one clock is in motion? Notice although both clocks are identical, the moving clock ticks slower than the one at rest. In order to understand why, notice the paths of the light beams. The light in the stationary clock travels up and down vertically, but the light beam in the moving clock must travel a longer diagonal path. Since both beams travel at the same speed, and the upper beam travels a longer distance, the stationary observer sees the moving clock run slower than his own. This slowing down of clocks in motion is known as time dilation. It should be stressed that a person moving along with the moving clock would notice nothing unusual at all. The clock and the flow of time would seem to progress normally. According to this observer, he is at rest, and the other observer is moving past him. According to him, it is the other clock that is running slowly. The flow of time in Einstein's universe is entirely relative.
Now let's revisit our starship and laser problem and reveal the second part of that resolution.
Okay, better idea.
Similar to the effect that motion has on time, there's a relativistic effect involving length as well. Any moving object is shortened along the direction of motion. This effect is known as length contraction. Length contraction is the second necessary consequence of Einstein's postulate that the speed of light is the same for all observers. We now know beyond all doubt that both length contraction and time dilation actually occur. With time dilation and length contraction together, we can now see the final solution of how Einstein's postulate allows the two starships to measure the same speed of light. As the upper starship passes, we see that the starship's clock runs slower than the one at rest. We also note that the starship itself is shortened or contracted. After 12 seconds elapse on the stationary clock, we see that only 9 seconds elapse on the moving clock, not the 6 seconds we assumed in an earlier example. But due to length contraction, the moving ship and all the rulers aboard are contracted just enough to make the measurement work. According to the crew, the beam of light travels 9 light seconds in 9 seconds. They now report that the light beam travels at the correct speed of 1 light second per second.
Does that really happen?
Sure does. Thousands of experiments have been done since Einstein stated his postulate. and every one has shown time dilation and length contraction are real and really happen.
Back in 1971, 4 cesium atomic clocks were synchronized and flown on commercial planes that circled the Earth twice, and then compared to the reference clock at the U.S. Naval Observatory. Sure enough, the moving clocks differed from the reference clock by exactly the amount predicted by relativity. Let's look at it a little differently.
Okay, let's do something really scary. Let's draw a graph of space and time. Just kidding. Jeeves, help me out, please.
Here's a graph of a car traveling due east at its maximum speed of 100 miles per hour. It is making no progress in the northward direction. All of its speed is going east. Now let's turn a little to the northeast. Even though the car is still doing 100 miles per hour, it is going less than 100 miles per hour in the east direction, because some of the speed is being used to go north as well. Space and time can be thought of in the same way. Everything in the universe is traveling through space and time at the speed of light, the maximum speed available. Picture time replacing east and space replacing north in the car example. If you were sitting still in space, not going north, you are traveling at the maximum speed through time, east. But if you start moving in space, north, your progress through time will slow down, since some of your speed has been diverted. The faster you go through space, the slower your progress through time. If you could travel at the speed of light in the space direction, you would make no progress in the time direction at all. Time would stand still, as it does for a beam of light. And if you could go faster than the speed of light, you could travel backwards in time. Remember, if different observers must always agree on the speed of light, then they must disagree on the components of speed. Time and distance. Time and distance both shorten for moving observers. These unusual effects of relativity, time dilation and length contraction, depend dramatically on your velocity. At everyday speeds, they are simply not noticeable. The fastest that humans have ever traveled is a few miles per second, a tiny, tiny fraction of the speed of which light travels, 186,000 miles per second. But in Einstein's universe, space and time are no longer absolute. There is no single time that exists for everyone in the universe, no distance in space that everyone can agree on. Space and time, like classical velocities, are only relative. Einstein preferred to think of a single entity, space-time, in which events and measurements took place. One observer might see two events as separated by a large distance, but occurring at almost the same point in time, while another observer views the same two events as occurring nearby in space, but far apart in time. While the individual space and time separations will be different, Einstein's equations allow the two observers to agree on the combined distance through space-time. It wasn't just our idea about space and time that were altered by Einstein's theory of relativity. Einstein also realized that we should have to reconsider the whole idea of energy. If we look closely at a proton in a particle accelerator, it is easy for scientists to see that only some of the energy that we apply actually increases the speed of the particle. The remainder simply increases the mass of the particle. The faster it goes, the heavier it gets. When it is traveling at almost the speed of light, almost all of the energy we apply just makes it heavier. That is why a particle with mass can never reach the speed of light. It gets heavier instead of going faster. This fact is summed up in Einstein's most famous equation, perhaps the most famous equation in all of science. E equals mc squared. Besides defining the energy of a body at rest, the equal sign also indicates that matter can be converted into energy, and vice versa. The conversion factor, the speed of light squared, is an enormous number. According to Einstein's equation, a tiny bit of mass can be converted into an enormous amount of energy.
I'm gonna guess that's they played a footage of a nuclear explosion.
But there is more to E equals mc squared than atomic bombs. The recognition that mass can be converted into energy made it possible to understand the source of energy of the sun and the stars, still a mystery in Einstein's day. It also paved the way for the exploration of the mysterious realm within the atom, and the discovery of a whole menagerie of new particles, created from pure energy in powerful particle accelerators. In the early 21st century, nuclear power plants provide about 20% of our nation's electricity, converting a tiny fraction of mass of each uranium atom into usable energy. Perhaps even more than his idea about space and time, Einstein's mass-energy equation has had a far-reaching impact on our world and our way of life.
True. And by the middle of the 21st century, fusion reactors fueled with helium-3 mined on the moon will convert even more mass into energy. And this will be with no dangerous byproducts.
Relativity is about two people agreeing about what they see when one of them is moving. When that motion is at a constant speed in a straight line, we say the observers are in an inertial reference frame.
Yes, Einstein's relativity for inertial reference frames is called his special theory of relativity.
And in it, he postulates that any person moving at a constant velocity will observe the same laws of physics that a stationary person observes.
I take it from your little performance that you're going to tell us about frames of reference that are speeding up or slowing down or changing directions.
Absolutely. Do you think that Einstein's principles still hold? Can we say the laws of physics are the same for observers in accelerated frames?
No.
Does light travel at a constant velocity in non-inertial frames of reference? Jeeves, start it up, please.
Let's put you in a closed room in deep space, millions of miles from gravitational influence of any planet. You can float about the room effortlessly. Objects at rest remain at rest. Objects in motion float along a straight line until they collide with a wall. But if rocket engines attached to the room began to accelerate you through space, you would feel something quite different. You would feel yourself pushed by the accelerating floor. Objects at rest would seem to fall as the floor accelerated up to meet them. If the acceleration were large enough, you would be able to stand and walk about just as you would if you were back on Earth, subject to the attraction of gravity. In fact, Einstein argued, there's no way to tell the difference between being stationary under the influence of gravity or being accelerated through space. And since all observers must agree on the basic laws of physics, the laws of physics that describe gravity must be, in some sense, equivalent to those that describe acceleration through space. According to the general theory of relativity, the presence of matter in the universe alters the geometry of space. One way to visualize what happens is to imagine a bowling ball being placed on a trampoline. The bowling ball distorts the surface, causing the other objects in the vicinity to move towards it. Something like this is responsible for the force of gravitational attraction. Even though we have been able to calculate the strength of gravity since the time of Isaac Newton, we never really had a clear picture of how gravity works. An apple falls to earth, we would say, because some invisible force of attraction between the apple and the earth pulls them towards one another. But what causes this gravitational force? How does this attraction happen? Nobody really knew. So Einstein did away with the idea of an invisible force altogether. There's no mysterious force pulling the apple towards the earth. Rather, the presence of Earth in space causes a curvature of the surrounding space-time, and the apple simply follows the most natural path available to it as it moves through this curved space. In this case, the path that causes it to move towards the Earth. If Einstein was right, and massive objects really do curve space itself, then gravity should affect the motion of everything through that space, even light. Imagine the light from a distant star traveling past the sun. According to Isaac Newton, gravity is an attraction between all objects with mass, and since light has no mass, the star's light would be unaffected by the sun's gravity. But in Einstein's picture, a massive object like the sun bends space itself. So starlight moving through the curved space should be bent by gravity. Who was right? It would be hard to tell. The deflection of light predicted by Einstein's equation was tiny. And besides, you can't see the light from stars that lie behind the sun because the sun is too bright. You need to be able to see the stars in the daytime. Luckily, just 4 years after Einstein's 1915 publication of the general theory of relativity, there was a solar eclipse due to occur across the Atlantic Ocean from northern Brazil to the coast of Africa. Astronomical expeditions were sent to both of these locations, equipped with telescopes and cameras to photograph the stars as they become visible behind the blotted out sun. If Einstein was right, the apparent positions of these stars would be shifted away from their true positions photographed months earlier, when the sun was in another part of the sky.
The result? The astronomers announced that Einstein's predictions were confirmed. Relativity was quickly accepted by scientists, and it wasn't long before Albert Einstein became a household name. In the years after Einstein's theory of general relativity was dramatically affirmed during the 1919 eclipse, other scientists began to work out the implications of general relativity. Jeeves, you want to take over?
We know mass distorts space. We know light is affected by gravity. And we know Einstein's theory of general relativity makes possible one of the strangest objects ever imagined by physicists. If you could create a large enough distortion in space-time by placing enough mass in a small enough space you could create a region of space-time so strongly curved that nothing, not even light, could escape it. And since nothing can travel faster than the speed of light, anything that entered this region of space-time would be trapped there until quantum mechanical effects allowed it to escape. Black holes can come in any size and have any mass. All that is required is that enough mass can be concentrated to the point where it collapses under its own gravity. Stellar mass black holes are formed when stars 20 or more times the size of our own sun finally run out of fuel in their cores. They rapidly cool and collapse, and the shockwave from the collapse blows the outer layers of the stars to bits in a colossal explosion called a supernova. But the small, dense core of the star can remain bound together by the force of gravity. As it continues to collapse inward under its own weight, the atomic particles of the core are smashed together until all that is left is a black hole. In its center lies the singularity, the mass of an entire star crushed into a single point in space. Surrounding that is an invisible shell called the event horizon. This is the cosmic point of no return. Once inside the event horizon, nothing, not even light, can escape except through quantum mechanical processes. Supermassive black holes may contain billions of times the mass of our sun. These monsters lie at the center of every large galaxy. Micro black holes have tiny masses at which the effects of quantum mechanics are very important. Black holes of this type have been proposed to have formed during the Big Bang and would quickly evaporate due to said quantum mechanical effects. At the end of their life, it is believed that they would emit a sudden burst of energetic particles, but no such bursts have been detected as of 2008. We can never see into or directly know about what happens inside the event horizon of a black hole. In effect, any object that crosses this imaginary line has left our universe for good. But if nothing, not even light, can escape a black hole, then how do astronomers manage to detect them? It is possible to imagine spotting a solitary black hole by observing the bent starlight from behind it. But a better chance of detecting one would arise if they were not alone in space, but accompanied by another star. This black hole is drawing matter from a companion star, which orbits it at a distance safely outside the event horizon. As the gas spirals into the black hole, it heats up and emits huge quantities of high-energy radiation. Intense radiation emerging from a small area, or stars orbiting small invisible companions, these are telltale calling cards of a black hole. It may seem surprising, but today, more than 100 years after Einstein published his first papers on relativity, there are still aspects of his theories that have not been put to experimental test. One is the idea if that there were a very violent event in space, such as a collision of two black holes, or a supernova explosion, that it would cause a ripple in the space-time fabric. By the time it got to Earth, the ripple would be minuscule. But scientists hope that with sensitive experiments, they might someday be able to detect the tiny distortions of space caused by these gravitational waves. Another prediction of general relativity, not tested until this century, is related to the effect of rotating objects on space-time. While a massive object only bends space in its vicinity, a spinning object will also twist the fabric of space. This was recently confirmed. Yes, Einstein's legacy is sound,
Let's see.
and his achievements place him alongside
No, it's
Galileo
not.
and Newton, as well as a small handful of scientists who completely changed our way of viewing the universe and our place in it.
Hey, shut up. Alright, so that was the Cassiopeia project, quantum electrodynamics. And, I don't know. Oh yeah, by the Ryan Antkowiak. Anyways, I don't know if it's by him or that's just the channel that it's being hosted on. But, hold on, let me just do that. That's it for today's little short stream. You got to kill a lot of puppets, waste a lot of ammo, and build the wall. I'll almost finish the wall all the way. I still need access to the forest, but I don't know. Even the internal wall is getting fairly finished. Let me see this. If I can place it anywhere on this door frame, probably it would have to be here. Seems like it. But anyways, that'll be it for today's stream. Tomorrow we'll continue the adventures of Bob doing buildy stuff, because, you know, he likes to build stuff. We like to build stuff while we listen to sciencey stuff. Anyways, that'll be it for today. And I will see you all